Okay, all right. Welcome everyone. We'll kick off the third day of this RL bootcamp. The first 2 days, if you attended or watched the videos, were I hope what is sort of core RL from a CS perspective, planning, online, offline. Hope you've seen gotten a good coverage. The last 3 days are going to be disciplinary perspectives from 3 disciplines that we feel are closest to RL: statistics, control theory, and operations research. So today we're very fortunate to have Eric Laber from NC State giving us a tutorial on statistical inference in RL. Now RL, a lot of roots go back to stats, including giants like Blackwell and Lai and Robbins, and within our generation, Susan Murphy and Eric himself, who got his PhD working with Susan here at Michigan, where I am. And Eric has been a real leader in this field of dynamic treatment regimes, which includes techniques from RL and from causal inference and from semi-parametric efficiency theory, and tries to address decision-making problems in really complex scenarios that arise in healthcare, especially with high amounts of noise and little signal, and you have to design your study carefully and do statistical inference and build confidence intervals. And some of the more statistical topics started to emerge in Emma's talk in her tutorial yesterday when she was talking about offline data analysis. And she also mentioned healthcare and education as application areas. In these areas, we don't have simulators usually. We have lots of noise, lots of variability. And I feel like in these domains, having a statistical viewpoint is even more important than maybe in some other RL applications. So welcome, Eric. Take it away.
Well, thanks everybody for coming and giving me the chance to talk here. And thanks to Ambush and the organizers. A lot of this draws from previous talks or papers, and so a lot of this is the work of my students or postdocs or collaborators. You can learn more about them, their bios on my webpage. So I wanted to start by giving a little bit of introduction and background, and which will also reveal kind of my own biases. So if I make a statement about that seems very general, it's really only general kind of in the world I work in. And so I hope nobody takes offense or says that's not really the way it is, because they may be working in an area that they're not familiar with. So I'll try not to speak too much in generalities, but I just wanted to sort of say up front the kinds of problems I think about, which frames the way I sort of think about problems and the way that I describe them. So my own research focuses on methodological development for decision-making in really data impoverished settings. So these are generally not high volume settings, or at least they're not, the signal to noise ratio is often small. So as Ambuj mentioned, I work a lot in precision medicine, precision public health, logistics, and sometimes the data volume is high, and I'll go through 3 examples in a minute. The signal may be weak, which means that we still have substantial uncertainty. And often collecting more data is not inexpensive. So if you're talking about a clinical trial and each data point is a patient, that can be extremely expensive. Or if we're talking about, say, building a fulfillment center in a logistics problem, also each decision is very expensive. And so in these areas, statistical inference is critical because there's so much uncertainty. But also, as I'll talk about, there's a lot of work now in bringing RL into more like sort of critical problems where RL hasn't been used before. And so the reality is that there's kind of a panel of human decision makers who want to use data to inform their decisions, but they're not ready to sort of hand complete control over to some kind of automated system. And so we need to provide them with uncertainty estimates and give them confidence and help build trust so that these systems can be adopted and used in the real world. And so what we're seeing is that inference is playing a really critical role for getting that kind of buy-in from domain experts. So these images here on the bottom, I'll go through, they each correspond to an example. So the first one is kind of a classic biostats example, an adaptive clinical trial or response adaptive clinical trial. And while I'm mainly going to focus on inference, I want to sort of give the context, set the stage for some of the methods. So one of the trials we're involved in now is iSpy 2+. And so this is an adaptive platform clinical trial for breast cancer. And I realize not everybody's a clinical trialist. And so what does that mean? What it means is that patients are coming into the trial and you're assigning them to treatment with probabilities that adapt to the evolving information, so the accumulating information. So you look at the responses of previous patients, and you look at their biomarkers, and you adapt the probabilities. So the idea is that we want to give you treatments. We want to be more likely to give you a treatment that's going to benefit you. So those working, well, even if this is all new and you've sat through the tutorials, you'll certainly have heard of Thompson sampling, which was motivated by this very problem where patients were enrolling and they wanted to adjust the randomization probabilities to 2 treatments to try to benefit patients in the trial. A platform trial, and this kind of trial in particular, is more complicated in that new therapeutics are being introduced and removed from a pool over time. So this becomes a very complicated setting where you are getting information, but then a new therapeutic comes in which you have no prior information, or you have some prior information, and patients are randomized multiple times. So this is an example of a kind of a bandit type problem, but there's complex dependence across the patients, so they're not really independent as they come in because of the randomization probabilities. And also we want to do inference. So we're doing all this kind of adaptive randomization, but inference becomes very complicated. So the goal here is to optimize health outcomes for both the in-trial patients and the future patients who would benefit from information generated by the trial. So this is this kind of duality between sort of exploiting what you know now and trying to learn so that you can make better decisions in the future. So the kind of questions that we'd want to answer, how should we tailor treatments to the evolving characteristics of each patient? When, if, and for whom does a given treatment work? So this is a slightly different question. So sometimes trials are sponsored by drug companies and they want to know, is there some subgroup that my treatment works best for? And what patient characteristics or biomarkers are really important for choosing treatment. So that's like generating new clinical insights into a problem. And just to give you a sense for kind of why this is such a mess, on the lower right-hand corner here, you can see the sort of schematic for the trial. So you have, in this arrow here, you have a new agent or a new therapeutic comes in. That forces you to update randomization probabilities for new patients. We have new patients coming in. We randomize them either to some kind of experimental condition or control arm. We observe an outcome. We update the probabilities. We have to apply certain termination rules to remove treatments from trial or to triage patients into different salvage therapies. So it's very complicated, but also we really have very limited data, and so every decision we want to make sure we're sort of maximizing information sort of accumulation. Okay, so this is one example. Another one, we were asked to look at how Ebola virus or how resources were allocated in the Ebola virus outbreak in 2014. So this is an example where we're sort of asked to look back at a strategy and do kind of policy evaluation. And so what we're looking at is the allocation of interventions over both space and time. So down here is a map of West Africa, and I have a color coded the infection from outbreak, which is sort of this dark, this green to red. And so it starts in Gukedu and sort of spreads out. And of course, the decisions you make are subject to logistical constraints and cost constraints, and you also have imperfect information. So there might be a report that there's sort of infections where there aren't any, and of course there are underreporting and so on. And so the kind of questions that we were looking to answer is, how should the interventions have been tailored to the evolving pandemic? Yeah, that's one question. And is an RL-based intervention strategy better than an expert strategy? And if so, how much better and why? So for those who have followed this, there's been enormous debate about how much was spent in the management of the outbreak and whether it was effective or not. And this has real implications for how we manage infectious diseases now. And obviously, this is something we can't quite ignore in our current state. So with COVID and so on. Okay, so this is another sort of example. And then I'll talk about two sort of other examples from industry. So this is something I work on. I'm an Amazon scholar, so I spend some part of my time at Amazon. And so one kind of interesting bandit type problem is bookstore assortment selection. So what books should go in the stores, right? And this of course happens at grocery stores, and it happens basically in any retailer. So you can ask, okay, well, what title should go in there? And there's some enormous action space. So there's like 100,000 titles that are like deemed acceptable. And from those, we want to choose something like 2,000 to 5,000, depending on the size of the store. And so, the set of actions is 100,000, choose 2,000, which is enormous. And this is known as a combinatorial decision problem. And of course, the goal, and you can tell that, it's important that we make sure Amazon's happy with things that we say about what we do there. So we want to make customers happy, of course. But then also you want to make sure that you are generating revenue, right? So the kind of questions here, keeping in mind that in a bookstore, previously, these decisions were all made by people, right? So there's these experts that go and decide what go in the store. And of course, there's interest in using RL because of the benefits it might bring in terms of just improving utility. But so obvious questions like, what's the optimal assortment? But how does it vary across space and time? How does it vary across, say, the Northwest versus the Southeast? And if we use an RL-based assortment, how does it differ from expert curators, right? So what are the key differences? What are the takeaways? And can we push that back into data-driven decision-making, done by humans? And how do we experiment efficiently and safely? And by safely here, I just mean without taking too much risk. If you have a really bad assortment, not only do you have low sales, but if people think they go into the store, they don't see things that they want to buy, they may not come back, right? So there's very long-term kind of consequences. So this is the kind of question in books, and this is kind of a classic big. You might think about this as a big data problem in the sense that you can leverage data from .com. Obviously, there's a lot of sales data there. Sorry, I should stop. I was pausing to read a question, but maybe I'll try to find a good time to kind of. I'll pause after the examples and answer the question so that I don't just stare blankly into the screen. Another question related to bookstores that maybe you might not have thought about, or I hadn't thought about at least. So you think about bookstores, you think about all this data, but there's this other issue, which where do you put the stores? So now we've gone from kind of a big problem to a very small problem. There's like 10 bookstores currently open in the United States. And so if we're looking at what locations to put them, do they go in malls, do they go in street corners, do they go in big cities, do they go in suburbs, where should they go? How big should they be? And of course, it's related to the assortment problem in that a good location requires might only be good if you choose the assortment correctly. But now we're talking about a very small sort of number of data points, and every action requires you to build a store, right? The action is put a store at a given location. And so now we're talking about, a big investment and a lot of legwork in terms of getting that in place and getting it constructed, signing leases and so on. The goal remains the same, but now, we look at the questions like which subset of available sites should be chosen. So some set of sites become available in a given city. Which ones should we either investigate further or go ahead and pull the trigger and build a store there? What makes that a good location? Is it foot traffic? Is it the number of, let's say, Prime members that are near the area? Is it the other stores that are around? Is it the type of jobs that people have? Is it their age demographic or something else? And how do we grow? So suppose we wanted to build more stores of a particular type, or some other company wanted to do that. How do we optimally grow? So we could build, let's say, K stores now, or we could build, K over 2 stores now and wait to see that data and then choose the next K over 2, right? And there's obvious trade-offs there. And so there's a lot of problems where we also want to attach uncertainty to all the answers that we give to the human curators. Okay, so I want to just pause and take the question. The question is, are these examples, do we find use for inverse reinforcement learning? And the idea being there, if we observe the decisions people are making, can we reverse engineer what reward process they were using or what kind of policy they were following? And that's a great question. And we do this in some applications. We've done this in some medical decision making, where we take observational data and we look at decisions that clinicians are making over time, and we would try to reverse engineer what kind of composite outcome they might be trying to optimize. And even if we think they're doing it imperfectly, try to then bound what the sort of optimal policy would be. In this context, you kind of do this ad hoc IRL, where you talk to the people and ask them, what is driving your decisions? And it's unlikely they're kind of implicitly solving an MDP in their head, but it is more likely that they are trying to sort of optimize immediate revenue. And then also, there is some experimentation that happens. So you might say, well, how are local offerings going to do? So should we have a section on like exploring Seattle in a store, for example? And they're kind of running those kinds of experiments. So it's mostly kind of myopic optimization with maybe a little bit of experimenting. And so that's kind of handcrafting, through human interaction, the reward function. But that's a great question about what you should be choosing so you don't end up optimizing for the wrong thing.
So Eric, I had a question about the first example of adaptive clinical trials. So you mentioned Thompson sampling goes back to 1933, and having an adaptive trial just seems like such a natural idea for a person who works with bandits and RL. Why are they not as common as one might think? Like, is it simply the logistical difficulties that you alluded to?
So that's a good question. So why aren't they the only thing we do? And there's been a bunch of debate in the clinical trials world about the ethics of doing this. In part, there's this idea that, well, if there's really equipoise, we shouldn't be changing the probabilities. But there's also this idea that there's certainly a mentality about, we're going to run a trial for a very short amount of time with a very small number of patients, and then we're going to take that information and we're going to inform the decisions we're going to make for many, many, many more patients. And so, if you imagine that we're going to have 100 patients in a trial, but then we're going to treat, let's say, 100,000 patients based on the information we accumulate, then there's this focus on generating as much information as possible in the trial. And often the thing that generates the most information is either complete randomization or adaptive randomization, but adapting for information gain and not for exploiting or outcome adaptive randomization to maximize outcomes. But there has been movement on this in terms of trying to formalize that balance, because I think the out of trial patients and the in trial patients aren't always so imbalanced as we'd like to think. Another issue is how challenging inference is, because once you start adapting the randomization probabilities to the accumulating data, then everything becomes messy. Sample size calculation becomes more difficult. Sort of ensuring you have correct inference becomes more difficult. So those are some of the reasons, especially with things where like treatments are coming in and out. But we do know how to do inference for bandits. So at least in certain cases, parametric bandits and so on. So yeah, that's the short answer. There's some historical reasons, and also there's some ethical reasons, and then there's kind of mental model reasons. Okay. So all of these examples, we looked at informing decisions that are typically made by people using reinforcement learning. And so obviously it's been used in areas like computational advertising and robotics and all sorts of interesting areas. But now it's showing up in places where we haven't used it before. So I'll call these high stakes problems, in that previously in whatever domain, humans thought these problems were too important to automate, or maybe they just couldn't automate. And so medicine is an obvious one. Precision public health is another one. Low frequency business decisions like opening stores or building like fulfillment centers or warehouses. Defense and intelligence is now getting into this. There's some pretty interesting stuff in terms of like, can you build decision support systems that will generate things a human wouldn't have thought of? So intelligence operatives are interested in that because they don't want a thing that agrees with them. They want a thing that will tell them a scenario or generate a scenario or a decision sort of path that their opponent might think of, or their, whoever the adversary is, that they wouldn't have thought of for the adversary. So some interesting stuff there. But as we look to transition to RL decision systems, we go to implement these things. We really have to build trust, and that's done by developing knowledge and uncertainty quantification. And so, at the heart of that is statistical inference, at least from my point of view. And so, having been in these discussions with clinicians and with decision makers in industry and defense, that's really critical to get buy-in if they're going to use the things that we build. Okay, so that's kind of the motivation. Here's an outline for the rest. And I also should point out that, I have like basically an infinite number of slides. And so I don't expect us to get through them all. But I kind of said that I was hoping we'd get through the first part, and then I would selectively talk about some of the stuff here based on interest. And I also thought it would be useful. I thought it would also just be useful to put this all in one place. And so if people were interested in something I didn't cover, they could go look at the slides. So like a lot of the simulation experiments, I may skip over, but I wanted to put them in there so that we could see their operating characteristics.
The question for you, Eric, could you say a little bit more on the low frequency business decision?
Oh, sure. So I think maybe I should just say the contrast I'm making. So I think about high frequency decisions as things like ads. So what ads do we display? Or what sponsored things do we display and on search on like Amazon.com? Those kind of things where you're making many, many decisions, and each decision kind of is so very high frequency of decisions, recommender systems and so on. but also the cost of any recommendation is low. That's not to say that a small change doesn't produce enormous volume and isn't important. But that's different than, say, building a warehouse. If you're going to build I don't know, one of these giant 100,000 square foot warehouses somewhere, it's going to be there for a long time. Or if you're going to build a Go store, it's filled with all this, computer vision tech and very expensive. Those are less frequent decisions. Or treating a patient that you see once every 3 months or once every 6 months. We've done this for like dentistry. So, when should you recommend that the person comes back to the dentist? Surprising that no one had looked at that before, and that the sort of come back once every 6 months recommendation goes back to like, I don't know, I can't remember now, 1890s or something, and just has never been updated. Obviously, if somebody has sort of bad dental health, they should come in more frequently. If somebody has good dental health, they should come in less frequently. But even big companies like Health Partners don't do that. And so we worked on that a little bit with them. So that's what I meant. Hope that helps. Okay. So in terms of this outline, I'm going to start off with this sort of toy problem, which is the max of means. This is a well-studied problem in statistics. It goes back to the 80s at least, if not earlier. And the reason to look at this problem is it sets all the ideas. So then as we then look at a slightly more complicated problem, which is inference for the value function, we'll see these ideas popping up. And then as we look at the rest of these, we'll see basically the same ideas, just in more complex settings. Okay, so one question that came up here is, how do we see implementation of RL to autonomous critical safety systems? I don't know that I have I haven't worked in that area, and I don't know that I have a strong opinion there. Although I will say the one area where we've worked where safety is really important is in diabetes. So if you're looking at, say, the artificial pancreas type work, or things that are making recommendations for let's say how much insulin to take or what to eat before you exercise, there's real serious risk there, right? We work in type 1 diabetes. And so there we have done some work in RL, but having very tight error controls or risk of adverse event control. So it's kind of like Neiman-Pearson type decision-making in RL. But I haven't worked in like, robotics or autonomous vehicles or some of those things where I know there's been some innovative stuff in safety, but I don't know much about that area. Okay. So some notes on context for the rest of this tutorial. We're going to try to pick up the simplest possible settings to illustrate the technical challenges. There'll be a couple times where I do a little aside and say, okay, here's what would happen if we were like in an MDP setting instead of a one decision setting, or if we had some other kind of generalization. We're going to look at simple parametric models because those illustrate really the key points, and the idea being that you can use basis functions or other kinds of expansions to go to a non-parametric model. And we're going to generally, in terms of assumptions, we're going to generally avoid assuming the models are correct, especially since we're using these parametric models. And so when we talk about inference, we're often talking about projections of the true, let's say, value function or Q function or something onto whatever space we're approximating with. And there will be some regularity conditions that I'll make implicitly. So if I have an expectation of something, I'll assume that it exists. And so moments and that parameters are identifiable, and that, say, parameters are in the interior of a space or something, I probably won't say that. But the references will include all the technical conditions. And also, I'm not going to talk about the proofs unless I think it's particularly instructive. So I only have a handful of those. But I'll give references to the proofs because some of these proofs are long, but they're kind of more of the same. And so it's not really instructive to go through them, at least in the time that we have. I'm going to look at distribution theory, so mostly confidence intervals and testing. So I won't be discussing finite sample bounds. There are certainly people on this call that are much more qualified to talk about that than I am, but also in the applications we're looking at, a lot of it is really focused on confidence intervals and testing. Is this biomarker important for making a decision? Is this a good type of thing to offer in a store? That kind of thing. Okay, so the max of means problem. And I'm trying to do something here that might have been better done on a board, but we're not together, and so I may be spending more time on slides. But please ask clarifying questions because I know these slides are busy. We'll just try to go kind of through each line at a time, one at a time. So let P be some fixed but unknown distribution on RP. Okay, so some P greater than 2, because if P is 1, this is all pointless. And we'll define mu0 to just be the mean. So I'll be using this operator notation. So P of x is just the expectation of x. So it's the integral of x against the distribution here. And we'll define mu0 to be the max, the component-wise max of this mean vector. So there's P means, one for each component, and we use this wedge notation for max. So it's just the max of mu0, 1 through mu0p. Right? So this shows up in things like if you have a K-arm, or in this case a P-arm randomized clinical trial, you randomize patients to each of those P treatments. You take their mean outcome, and then you say, well, if I pick the one that has the highest mean outcome, then that's which treatment I think is best, if higher is better. And so this would be the sort of performance of the best treatment in that case. But more importantly, it's just a mathematical kind of toy problem that illustrates all these ideas that we're going to get into with Q-learning and other reinforcement learning algorithms. So we're going to assume that we observe x1 through xn. These are IID draws from P. So these are each one of these is a vector in RP. And mu hat is just a sample mean. So I'll use this bold PN to denote empirical expectation. So it's just an average over the data. So it's just the sample mean. And then theta hat is just the max of the sample means, right? And so our goal is to make inference about theta 0 based on theta hat, right? And typically inference for theta 0 will be based on the limiting distribution of root n theta hat minus theta 0. And we know that for nice problems, root n times our estimator minus the estimand, or the truth, is normal, and we can use that for confidence intervals, or we can use the bootstrap. But it turns out in this case that doesn't happen, and that's because of this max operator. So I want to first kind of walk through how one might approach this problem and why one encounters problems or difficulties. Okay. In a 233 slide talk, there's a lot of letters to be used, so apologies in advance for using fractor, but that's what we had to do here. So for some vector nu in RP, define fractor u of nu to be the set of maximizers of this vector. Okay, so it can contain more than one element if we have no unique maximizer. Okay, so here's the first thing. So let's assume that we have sufficient irregularity conditions that Pn minus P times root n times x is normal. So that is, so just if this notation's unfamiliar, and this is just the sample mean minus the true mean scaled by root n. So it's just, in other notation, it might be x bar minus mu times root n is normal, right? So this is true, as long as you have second moments. So this is the nicest statistical problem that we have, right? It's just the sample mean minus the true mean. Okay, suppose that's true. Then if we look at root n times theta hat minus theta 0, it converges to the max over the set of maximizers of mu0 of these zj's, where zj has the same distribution as, the same limiting distribution as x bar. So it's normal, mean 0, variance, covariance, sigma. Okay, so I'm actually going to go through the proof of this just because I think maybe it's helpful. It's only one line or two lines. So to see why this is true, let script en just be the indicator that you made a mistake. So it'll be 1 if the maximizer of your sample mean is not one of the maximizers of the true mean. So in particular, it's an indicator that the max over k k not in the set of maximizers over mu0 over the sample mean is in fact bigger than the max over the set of maximizers of mu0 of the sample mean. That is, if you take the argmax of the sample mean, you won't get a maximizer of the true mean, so you've made a mistake. Then you can show that this is little op1. Why? Because there's only p of these things, and there's a gap between the maximizers, their mean, and everything else. And so eventually you'll figure that out, and you won't make any mistakes. So if we write down theta hat minus theta 0, we can write it as the max of root n mu hat minus theta 0 if you get it right, or this difference if you get it wrong. So if you just look at this for a minute, and you'll see that if this thing is 1, then this term here, you guys can see my mouse, is that right?
Yeah, I can see your cursor. Yes.
Okay, yeah, great. So this term here will just cancel with this term and you'll be left with this. So if you make a mistake, you'll be maximizing over the wrong set, the set that doesn't maximize mu0. And if you don't make a mistake, you'd be maximizing over the set of maximizers, so you get this term. So this is just, so these two things are equal. But what's convenient about this form is that we know this term's little op, 1, and this term here is bounded by mu hat minus mu0. If we take the sum of mu hat minus mu0 absolute value times root n, that'll be an upper bound on this. You can just use the triangle inequality to get that. So what you end up with is the max over this first term. And I use the fact that when j is in this set of maximizers, theta 0 is in fact the same, is the jth mean. These two things are equal because j is a maximizer. So you just get root n times mu hat minus its mean. And then you have the max on the outside plus some term that goes to 0. And so this thing here is going to converge to the limit we stated in the lemma, right? So this thing will go to a normal. All the components over j will go jointly to a normal. Then we'll take this max to use continuous mapping theorem. So the idea is that we get this limit, but it depends on this set, right? With the set which we don't know. And so what can we do about this? And why is this even a problem? Okay, so it tells us that root n theta hat minus theta 0 goes to this max of zj. Well, we can certainly estimate zj. The problem is we don't know this, right? And the limiting distribution depends abruptly on mu0 in the sense that if we change mu0 by a little bit, we can change this limit a lot. So for example, if p is 2, so there's just two means, and suppose that they are equal, so they're both equal to 0, so the argmax is two components, and suppose that sigma is just the identity, so everything's independent, then the limit would be the max of two independent normals. That would be the limiting distribution here. But if instead we change the true generative model to be 0 and epsilon, where epsilon is some arbitrarily small number, like let's say 10 to the minus 20, then the limit, the asymptotic limit, would be standard normal. So if we wanted to use, maybe I should say this too also, which is that why do we care about asymptotic approximations at all? We care about asymptotic approximations because we want to make inference for this thing. We want to estimate the finite sample distribution of this quantity so we can make inference for theta 0. That's why we care. So if this thing does not faithfully reflect the sampling distribution of this thing, then we can't construct confidence intervals or do tests that have the correct operating characteristics. Okay, so what does this tell us here? It tells us that one asymptotic approximation is the max of two normals. The other one is a standard normal. And the difference depends on this arbitrarily small constant epsilon. And so that's really problematic. Which one should we use, right? So the asymptotic distribution depends on the maximizers, but it doesn't depend on the gaps. But intuitively, it should depend on how close those two means are to each other, or in general, if you have p means, how close they are clustered to the maximizer. And this is really problematic because the finite sample behavior of this thing will depend critically on how big the gaps are between the means. And I'll show that in the next slide. But there's a question that came in that said, here am I assuming the dimension is fixed? Yes. So for illustration, we're assuming the dimension is fixed. You can look at the p diverging with n case, and things can just get worse, essentially. Well, okay, I should say it depends on how things diverge, but you can imagine a case where like you keep getting a piling up of means getting closer and closer to the maximum. And so whatever problems arise here will certainly arise there, but you'll have additional complexity in terms of estimating the means, for example.
May I ask a question?
Yeah.
Yeah, so I'm really wondering about how serious is this problem in the finite sample case, because it seems that what's happening, and this is kind of typical, that if you're taking a limit in one of the variables, then you see some phase transition, like some really sharp transition happening. But if you're not taking the limit, and I assume that everything is much smoother.
Yeah, so this is a good question. So, two things. One, I'm gonna show you an example on the next slide with the finite sample behavior. In normal problems, in standard problems, that's exactly what happens. In that things are smooth and we don't have an abrupt change in the limit, and so things work out. But here we do. This abrupt change is not It's not something we normally see in a regular statistic, and we'll formalize that in a minute. But the issue is that if we wanted to do so you might say, okay, well, I don't want to use this directly. Maybe I just want to bootstrap this thing. And if I just bootstrap this, maybe that will work, right? The idea is if this finite sample thing is smooth, maybe I can bootstrap it or somehow perturb it and do inference if I don't want to try to use the actual asymptotic approximation. We'll see that that doesn't work either. But the reason that this is problematic is we have to use some limit to make inference. So the natural thing to use then would be to assume a unique maximizer, I think. So you have to pick this set to do inference, right? If you're going to use this approximation, we can definitely estimate sigma, right? We can estimate sigma by the sample covariance, that's no problem. So then we have to then use this. If we're going to use an asymptotic approximation, we have to use this thing, which means we have to pick something for this. So a natural thing is to pick this as just a singleton and use a standard normal. We'll see that doesn't work very well. And if you, otherwise you have to kind of guess at a set, which then becomes more difficult, whether you're going to pick, say, well, if just two, maybe to say they're both maximizers, but if you have, say, P, it becomes more difficult.
Yeah, so I guess what you're saying is that standardly we like to rely on asymptotics, even in the finite sample regime, trusting that somehow the asymptotic is going to kick in anyway soon enough, and that's good. And even bootstrapping is going to rely on something like that, unless you apply some really big corrections. But those are like really technical and challenging, and to keep the coverage good, it's going to be very, very challenging. So altogether, what this means is that the standard tools and standard reasoning is not really a good fit for this. That's what you're saying.
That's right. Yep. And yeah, exactly. So yeah, thank you. And I'm even going to show you what happens if we do this now. Yeah, great, thank you. So let's look at an example. Suppose we have data from a normal distribution, mean mu0 and identity covariance, so their components are independent. And we'll assume that mu0 in fact has a unique maximizer. So this is a setting where we have a unique maximizer, which means that if we go back to this would just be a singleton and the limit would be normal. I shouldn't have said, yeah, okay, the limit would be normal. And we'll assume that just for notational convenience that the biggest one is mu1 and it's greater than muj. So first, because everything is normal, we can actually work out what's the CDF, the finite sample CDF of this thing, right? So if everything is normal, then the probability that rho n theta hat minus theta 0 is less than t is the CDF of a standard normal. That's what its asymptotic limit will be, times the product from j equals 2 to p of t plus rho n theta 0 minus mu0. So this is going to be that gap. And so the issue here is that, as you can see, that this gap here is positive. So as n goes to infinity, this thing goes to infinity. Each of these terms goes to 1, and we in fact get this as our limit. But this can be very far from the asymptotic limit theta t when the gaps are small relative to rho n. Right? So these things here could be non-trivial, right? And so they can contribute substantially to this limit. And if we look at it at a simulated example, so here I set p equal to 6, n equals 100, and I set mu0j to be the maximizer minus delta, and I have three different values of delta here. Delta equals 0.5, 0.1, and 0.01. And the histogram is just the actual finite sample distribution of theta hat minus theta 0 times rho n. The red line is a standard normal, which is the limit. And you can see that if this gap is big, 0.5, so we'd have power like 0.9999 to detect this difference. Then this asymptotic approximation does great. So we could construct a confidence interval for theta 0 based on this normal limit, be no problem. But if I change it to something where I have lower power, I think the power here is about 0.5. Although I should check because I don't quite remember. Now you see this big shift. And so if you look over here, we have this, well, as expected, the max has positive bias, and so it's shifted upward. The sampling distribution is shifted upward. And so we could end up with very poor operating characteristics if we tried to get a lower quantile, for example, here. And of course, if we set this to be really small, then you know, and if we went to the extreme case, we could make them almost non-overlapping. Of course, they'd have to overlap because it's a normal distribution, but essentially the amount of overlap could go to 0. And so what this means is that if we just take the norm, so here's n equals 100, and if we took a normal approximation, which is actually the correct limiting distribution, the finite sample behavior does not match the limiting behavior. And so we have this big mismatch. And so that's the problem. So if we constructed a confidence interval using this case here, our coverage might be quite far from nominal levels. I hope that helps, Chapa, sort of drive this point home. So, okay. So this is what we would call a fixed parameter asymptotic evaluation or analysis, meaning that we fixed theta 0, and then we took limits. And the problem here is that it doesn't account for uncertainty in factor u of mu 0. It doesn't account for uncertainty in this argmax set. We don't know what this set is, but in the limit, in asymptopia, we know this set with probability 1, meaning that we can test whether mu 0j is equal to the maximizer with power going to 1 as n diverges. And so there's this mismatch between the asymptotic framework, which says we will know what that set is, and the finite sample behavior, which says we don't know what that set is. And we need some kind of asymptotic framework that retains this uncertainty or this instability about the set as n diverges. So we want an asymptotic framework that will allow us to incorporate this uncertainty and identify sensitivity to this uncertainty. And the way that this is done is using what are called moving parameter or local parameter asymptotics. And the idea is we want to have a sequence, we want our methods to work under a sequence of generative models where the features of the sampling distribution are retained asymptotically. What I mean is we want this instability about the argmax set to sort of persist no matter how big n gets. And this is a common thing we see when you study the power of hypothesis tests. We know that any reasonable hypothesis tests will have power going to 1. So how do we compare them? We look at sequences of parameters approaching the null. And the same idea is happening here as we look at sequences of parameters that are getting closer and closer to the max. And more generally, we're going to look at 1 over root n perturbations of the underlying generative model, and we'll study the behavior of, say, an asymptotic approximation under such perturbations. So to do that, we're going to look at an IID draw, say xn1 to xnn. So for every n, we get an IID draw of size n, but now it's from a distribution Pn that changes with n. And we're going to assume that the mean under this distribution Pn, which we'll write as Pn of x, is the mean under P plus S over root n. So this is called the local parameter. And so it's in a local neighborhood, a 1 over root n neighborhood of mu 0, but as n increases, then we'll get closer and closer to mu 0. So the idea here is that we can have a unique maximizer in mu 0, and we'd also have a unique maximizer for Pn, but we also have that some of the near maximizers are going to stay within a 1 over root n neighborhood. So our power to detect them or detect a difference between those near maximizers and maximizers never goes to 1. That's the idea. And we'll define theta 0 n to be just the max of mu 0 n, okay, as before. And apologies for the triple subscript. I try not to do that too often. Okay, so we're going to now look at what happens under this kind of sequence of generative models as a way of studying asymptotic approximations in this context.
So Eric, just so that it's clear, I'm just a little bit confused. So the problem you mentioned was occurring with sort of the natural estimator, which is just a plug-in, right? Just plug the individual estimates into the max. And I'm assuming that you cannot just get away from the problem by somehow redefining the estimator, but just wanted to be clear that that is the case.
Yes, that's a great question. In fact, I have it as an FAQ at the end of this thing. So at the end of this section, I have FAQs, and that's one of them. It's like, well, maybe we just shouldn't use an estimator. Maybe we should use something else, right? And it turns out the problem is with the estimand, and so there's no avoiding this problem. Yeah, that's a great question. Okay. So what happens if we look at things from this lens through the moving parameter sort of framework? And I should say that this is commonly done in as I mentioned, statistics for non-regular problems and testing, econometrics for weakly identifiable problems, and so on. And it can reveal when there's issues. And so what it does is it allows us to have these gaps between the maximum and the other means to shrink with a sample size so that we have uncertainty about this set, no matter how big n gets. So let's look at the same lemma under this now moving parameter asymptotic framework. So let S be fixed, that's the local parameter. And assume for every n that these x and I are drawn IID from Pn, and that they satisfy this condition. So the mean under this distribution, the sequence of distributions Pn is the mean under P plus a local perturbation. And we also assume that root n Pn minus, sorry, the empirical expectation minus Pn of x. So the sample mean minus the true mean under Pn also converges to a normal. So things like the mean are insensitive to local perturbations. That's why they're called regular quantities. And so this holds, again, under just second moments. This is a very weak condition here. And if you want to convince yourself, just take data from a normal distribution and take the sample mean minus the true mean under a model like this, and you'll see that this local parameter cancels and it doesn't depend on the local parameter. But if we look at the limiting distribution of theta hat minus theta 0 under this model, then what it converges to, sorry, this should be theta 0 n, apologies there, theta 0 n here, is we get the max of zj plus the local parameter minus the max of the local parameter. So what we see is this local perturbation now shows up in the limit, right? And so what that means is the asymptotic, which we already knew, but the asymptotic approximation is sensitive to local perturbations of the generative model of size 1 over root n. And that's important because if we use a plug-in estimator, we're plugging in, say, mu hat in place of mu. And mu hat is like a 1 over root n perturbation of mu. So normally when we use plug-in estimators, we plug in our estimate, in place of the true parameter. But the idea is they're insensitive to that little bit of uncertainty. And so everything works out. But here, it's saying if you perturb the true parameter value by a small amount, a 1 over root n amount, then the limiting distribution changes dramatically. And that's exactly what we're trying to do by plugging in mu hat in place of mu in that max, right? So this is why plug-in estimators don't work for non-regular problems, because it's sensitive to the kind of perturbations or the kind of uncertainty that's in the estimated parameter, which normally we wouldn't have. So the fact that this S shows up in the limit tells us this is a non-regular problem. So the definition of a non-regular problem is one in which the local parameter shows up in the asymptotic limit. So that's actually the definition. But this is what signals to us that there's a big problem in terms of using like a normal approximation or the bootstrap, and that those things are going to be inconsistent. So suppose we wanted to do inference. So what's the idea now? So the idea is we want to conduct inference for theta 0, but we want it to give correct coverage under models of this form. And the idea is that if we do that, if we can show that we give correct, say, coverage or correct operating characteristics for a test under these models, and we're insensitive to these perturbations, then it will perform well in small samples because it'll be insensitive to small perturbations again, and it'll be like a regular problem. So we want to design inference methods that are deliver the correct coverage or operating characteristics under these kinds of models. That's the idea. So how do we do that? Well, so I think I said all this already. So here's our limit. So it depends on the local parameter S. That's the definition of non-regular. And this is what signals that we're going to get poor performance from a standard asymptotic approximation based on fixed parameters. And bootstrap and series approximations are invalid, meaning they don't converge. The quantiles won't converge. So inference will be incorrect if you don't modify them somehow. And this kind of problem shows up everywhere in decision problems because we always have this max operator. So I know that we saw stuff on bandits and on MDPs. And so, if you think about the Bellman optimality equations, there's this max in there. We saw that in this very simple toy problem, you have a max of means. And so anywhere you're making a discrete decision, you commonly encounter this problem, I should say. So how do we conduct inference procedures that are valid under the moving parameter asymptotics? And the simple problem with the idea that we can then generalize them to more complicated problems, which we'll do in the remainder of the workshop or the tutorial. So
maybe perhaps naive question. So why is the non-regularity defined in terms of what happens under the local parameter setting? Why not just say that you have some non-differentiability? Why is there not a simpler definition of non-regularity? Am I missing something basically?
So I don't know the motive. So that the definition comes out of semi-parametrics. This is how they define it, because I think in general, if this happens, you don't have this nice regular asymptotically linear expansion of like sum of influence functions. You don't have that kind of expansion when this happens. And so I don't know if that was the right choice. I mean, they're one and the same in the sense that if you have a non-differentiable functional, you can't construct a regular estimator. But I think there are also settings where it's not so much that the function, okay, maybe this is the reason. The reason that to define it this way is to consider something like the lasso. If we have the lasso and the estimate is the coefficient indexing the linear model, that coefficient vector is not a non-differentiable functional degenerative model. It's a nice functional, right? But once you put that penalty on there and we start talking about, putting a lambda hat here, and this is a lasso estimator, now the limiting distribution of that thing will be sensitive to SJ. So, which then you might think this contradicts your previous question, which is that the lasso is an example where you could choose a different estimator and get a regular, right? This OLS estimator would be an example, right? That's a regular estimator, behaves nicely. The max of means, the problem arises with the estimate and you can't choose a different estimator. But that's one reason, because sometimes the choice of estimator will make this non-regular. Yeah. So, yeah, good question. I don't know if they were anticipating all of that, but the definition comes out of symmetrics anyway. At least that's where I first saw it. Okay, so what's the simplest thing that you can do? Well, this is a sort of building block idea, which is often a starting place for developing inference procedures, and that is a projection interval or projection confidence set. So we want to use the fact that mu0, remember mu0 is just the mean. That's a nicely behaved parameter, right? That's the easiest that's the first thing we learn about in statistics. So we know that that thing's nicely behaved. And we also know that theta 0 is just a function of this nicely behaved parameter, right? So the idea is maybe we can do our inference for mu0 and then kind of propagate it back through. And that's exactly what a projection set does. So in particular, a projection confidence set for the max of means is constructed by first constructing a 1 minus alpha times 100%, say, confidence region for mu0. And you can do that with just a walled interval. So here I've just given a walled type confidence interval, set of mu's such that n times mu hat minus mu transpose. This is the estimated covariance. Inverse times mu hat minus mu is less than some, let's say, chi-squared distribution, the percentile of a chi-squared distribution. So you get a walled type region for mu0, and this thing is nicely behaved. It contains mu0 with probability 1 minus alpha, both under the fixed and moving parameter asymptotics, again, because the mean is nicely behaved. So then what you do is you say, okay, well, I have this confidence set for the means. I'll take every vector in that confidence set for the mean, and then I'll just take the component-wise max of it, and then I'll take the union of all of those. And so that's a projection set for theta 0. So gamma n 1 minus alpha is going to be this confidence set for theta 0, and that'll just be the set of thetas in R, such that theta is the maximizer, the component-wise maximizer for some vector mu, where mu is in this confidence set. And to see why this will in fact give you correct coverage, whether you're looking at local or fixed parameter asymptotics, we just need to work out how we can make a mistake. So again, this is one of the very few proofs. It's only one line, so it seems like it might be feasible to go through it. So the error of this set is, well, that's the probability that theta 0 is not in our confidence set. Well, how can that happen? Well, it cannot be in our confidence set, and our mean might not be in our confidence region for the mean, or it's not in our confidence set and the mean is in our confidence region for the mean, right? So let's look at the second case first. So if mu0 is in this confidence region, then this can't happen, right? Theta 0 has to be in this region. Why? Because that would mean mu0 is here, which would mean that the component-wise max of mu0 is here, which means theta 0 is in this set. So this can't happen. So this term here is 0. And now that leaves us with this first term. And this first term is bounded above by just the second component, right? The probability of A and B is less than the probability of B. So we'll just look at the probability of this. So it's just less than or equal to the probability mu0 is not in its confidence region, but that's a standard, nicely behaved confidence region. So its error probability is less than alpha plus little op1 or also little opn of 1, either one. So we get correct coverage under both local and fixed asymptotics, right? So the pros and cons in terms of these kinds of sets. Well, first of all, it's a great starting point. So if you can work this out, then often you can develop more refined, sharper type results. But it's robust, it's general, it's conceptually simple. I mean, you're able to prove it in one line. The problem is the cons, this is kind of the pro, but the con is that it's minimally adaptive in the sense that it doesn't really rely in any way on how big these gaps are, the gaps in the components here, right? It just takes this big union regardless of how well separated the maximizer is. And that means it can be extremely conservative in some settings. And so, in some toy problems, you can sort of show that this is going to be, twice as large as a sort of bootstrap-based interval in a setting where you've done this, but you could have used a bootstrap interval. So a natural question then is, well, how do we improve on this? Well, another idea is to use bounds. So the idea here is we take something like the max of means, or we take something else that's non-smooth or non-regular, and we just sandwich it between two regular things. And those regular things we can bootstrap or use normal approximations and do inference for. And if we can get the quantiles of the bounds, they have to be quantiles. They have to bound the quantiles for the thing that you're bounding, right? So maybe I said it better here in this bullet. Just we'll sandwich the non-smooth functional, or the thing like the max of means, between two smooth bounds, and then use a bootstrap or series approximation on the bounds. And these bounds are going to be constructed by taking a sup or an inf over local perturbations. So the idea is, if we want something to be insensitive to local perturbations, a natural way to get that is to just take a sup or an inf over all the local perturbations, and then it has to be insensitive by construction, right? And I realize we're running out of time. I only have a couple more slides in this section, and maybe we can stop there for our break. Would that be okay? We ran just a tiny bit over.
Yeah, couple minutes would be fine.
Okay. So these will be valid under moving parameter frameworks just by construction. And they have to be the smallest possible among the regular bounds, in the sense that you could always construct a sequence of local perturbations to attain the sup or the inf. So you can't really be any smaller in that sense. And they'll also be necessarily adaptive, because if the thing that you're bounding is regular, meaning it doesn't depend on the local perturbations, then it would be a regular bound on itself. And you just end up resorting to like a bootstrap or a normal approximation. So what does that look like here? And again, let's go slow. I know this is a busy slide. So what we're going to first do is we're going to define a conservative, meaning overly inclusive estimator of the set of argmaxes of mu0. And we'll do that by just taking the set of J such the max over K of mu hat K. So that's the sample max minus mu J over some estimate of the covariance is not too big. So basically you say if mu J is within some tolerance of the maximizer, and you just choose this tolerance to be conservative, then this should include fractor U of mu0 with high probability. And so tau n is some tuning parameter that goes to infinity, and it's low OP rho n. And sigma hat is an estimator of this variance term. Okay, and now we're going to define a set of local perturbations, say S script S hat n of mu0. And this is going to be the set of vectors in RP such that Sj is forced to be mu0j if it's not in our conservative set. Okay. Now, this of course is not a thing we know, but we'll get to that in a second. So then an upper bound on root n theta hat minus theta 0 is the sup over all S in this set of mu hat minus mu0 plus Sj minus Sj. And the way that you get this is
Eric,
just by
clarification question. K here, so it's like we're kind of getting a gap. Is that right? K is, these are the different different means. So K versus.
Oh, you're right. Sorry, that should be K equals 1 to P. I should have written that out. You're right. That's exactly right. So it's basically looking at the difference between the maximizer, the sample mean, and then oh, this should be a hat. That's what was confusing. That's my mistake. There should be a hat here. Let's see if I can draw it. There should be a hat.
So it's the empirical difference between the empirical gaps, basically.
Yep, that's it. Yeah, hat right there. Yeah, thanks. Sorry. Yeah, good point. So that should be a hat. Yeah, that was probably very confusing. So there should be a hat there. And then the upper bound is the sup over these perturbations of mu hat minus mu0 plus Sj minus the max of Sj. So some things to note here. If I just set Sj to be mu0j, then they cancel out, and I get the max of the sample means minus the max of the means, right? So by taking this sup, as long as the sup contains mu0, that this has to be an upper bound. You'll also notice that if I bring this root n in here and recognize that when S is not constrained, it can be all of R, Sj can be in all of R, we end up with what's going to look like the limit under local perturbations. This term here will go to once I scale up by root n, we'll go to a normal, and then I'll have kind of the local parameter here and here. So it's as if I'm taking the sup over local perturbations. So this thing, it turns out, because of taking this sup here, now I'm going really wild with this pen, is smooth, and you can bootstrap it. So if we go to, oops, let me Oh, I can't advance the slide while I'm drawing. Hang on. Okay. If you go here, that's what this says. If U hat B is the 1 minus alpha percentile of U hat, and you construct a lower bound by taking an inf and call L hat B the alpha over 2 percentile of the lower bound of L hat, then in fact, this is a valid confidence interval here for theta 0, where you basically, it looks just like a standard confidence interval. You have the estimator minus a quantile, estimator minus a quantile, scale by root n, and you can show that this is in fact a 1 minus alpha 1 times 100% confidence interval for theta 0. And so that super inf smooths out this non-smooth functional, and you end up getting correct coverage. So some comments here. This set allows perturbations that are only near the, for the near maximizers. And that's important because we're not sort of affecting the unimportant parts. We don't want to be conservative in the parts that aren't near that maximizer. And this is very similar, at least in spirit, to the idea of a pretest in weakly identifiable problems in econometrics. So if you're familiar with that literature, they use very similar ideas. We also notice the local parameter only appears in components that are near the maximizers because we only want the sup and inf to affect those. And what this means is the super inf adaptively smooths root n theta hat minus theta 0, thereby making it regular. And an alternative to bounding and taking quantiles is to try to bound the quantiles directly. And this is an interesting idea. Ian McKeague has done a little bit of this. He's in the Biostat Department of Columbia for testing problems. And that's in general going to be less conservative, but it's also much harder to do. Finally, in terms of discussion, before I go to just some FAQs and then we'll break, the thing to remember here, the take-home message is that this non-smooth max causes instability. And if we just use fixed parameter asymptotics, this can provide poor approximations to the finite sampling distribution, which means it's hard to construct reliable inference procedures. If we look at a local or moving parameter asymptotic framework, this more faithfully captures this instability as the sample size grows large. And this makes it much more reliable if we want to construct confidence intervals or new tests. Projection and bound-based sets are two procedures that remain valid under local parameter asymptotics. And we'll see those again and again as we start to look at some more examples. I just had a few FAQs, if that's okay, or should we stop and do the FAQs after the break?
So I think officially we can stop so that people who have to leave and get a break, we can leave, but we can keep chatting. I'm still hanging around.
Okay, so I just had a few
questions on Discord or on Zoom, so I don't think there are any direct questions.
Okay, so here's good. Well, here's the question that I thought sometimes get asked in this area, and I think also just reflects some confusion in the literature. So the first question was already asked by Ambuj. You know, are there methods for inference that remain valid for non-regular problems? Oh no, sorry, you asked the next one. So are there other things besides bounding and predictions? Yes. So things like the M out of N bootstrap and subsampling are common. The one thing I think that's a real practical difficulty with these kinds of problems is that they're very difficult to tune because the subsample size is only sort of guided asymptotically. And there's some cases where if you try to use the M out of N bootstrap, it makes things worse. So there's an interesting paper by Richard Samworth in 2003 looking at the Hodges estimator. And are there any situations where you would need to use projection confidence set instead of the bound-based? I tend to favor the bound-based procedures because they're often less conservative. But there's some instances where it may be very hard to construct a bound, I think, especially if it's implicitly defined as an estimator. So that may be a case, although I will talk about one case like that. So generally, oh, there is one case. Yeah, there's another case, which is if you're trying to do sample size calculation, then sometimes the projection-based interval is easier because you're talking kind of before the trial is run. And so you want some kind of a smooth functional of the model that's easier to handle, in fact. So I will show an example like that if we get to it. Another FAQ. So why can't I just replace a smooth, non-smooth quantity with a smooth approximation? So maybe instead of a max, use a soft max, or I use bagging or sub-bagging to smooth things out. And so can I do this? Yes, but not really. So one of the earliest approaches for inference for the test error and classification, which has an indicator in it, so it's not smooth, or the marginal mean outcome of a treatment regime was to replace the indicator with a sigmoid or some other kind of, S-shaped function, either by just plugging in a sigmoid or by estimating with bagging or sub-bagging. But what you find is that the bias that's induced by this smoothing is really not negligible, and driving the bias down so that it doesn't dominate either inflates the variance or destroys local uniform convergence. And so this came up earlier, is that it's important to note that in this case, the problem is the estimand and not the estimator. So there's these impossibility results that show that you cannot construct a uniformly convergent estimator of the sampling distribution for a non-smooth functional. And so there's this work by Hirano and Porter, 2009, 2012. Vandervaart has a nice paper, 1999. Das and Sethuraman had this like 1.5-page paper where they show this thing where the variance has to go to infinity if you try to drive the bias down. That's the answer there. So then another thing is that has come up recently is, and there's been some work on this where people have tried to do the following thing. And so this is a strong opinion as opposed to maybe I just should qualify it that way. So why don't we just pick a different estimand? So why don't we just say, I don't care about the max, I care about the soft max, or I care about some other kind of smooth surrogate. And the reason is because those estimands often aren't interesting or relevant from a scientific point of view. So if a clinician is going to take the max of those means and use it, and we want to know how, what its operating characteristics are, its uncertainty is, then that's what we need to do inference for. So I think that's on us to figure out how to quantify uncertainty, not to change the estimand to something that's statistically more convenient. And so I guess that's maybe could be debated. Others may have different opinions, but I feel strongly that we should pick the estimand based on the science, the domain, and then work out how to do the uncertainty quantification. Okay, so another related FAQ here is that, okay, in real life, I know that no two means are equal, so that argmax set is really a singleton, so is this non-regularity just some kind of mathematical novelty? And I hope I've convinced you that that's not the case. Non-regularity signals that the underlying estimand is sensitive to small, and I say non-identifiable, meaning you can't identify them from the amount of data you have. In the generative model, so that asymptotic approximations are poor or could be poor in small samples. So in our example, we had a unique maximizer. So that set was a singleton, but we saw the asymptotic approximation was poor as it failed to account for gaps in the means, which were really critical to the finite sample behavior. And it's interesting to note that this same kind of thinking occurred in model selection, where there's this idea that if we have the oracle property, meaning we identify the set of important variables, and that the sort of limit distribution of the estimator is the same as if we had known that set ahead of time, then we could just do inference. But we know now, of course, that and it's been known for a very long time, that it performs very poorly because you don't know the set of important variables in finite samples, and that uncertainty is enormous. So there's this huge kind of set of papers by Potter and Lieb about this. It was known before that also, and now there's this whole industry sort of around inference after model selection. But it's the same. That was the same kind of thinking. Well, if we figure it out eventually, and we have a normal approximation, then everything should work out. But we know in finite samples that it's that's not the case. Okay, so I think we'll break there, and then sorry for running over, but I just wanted to get to the next part. So 1:30 or 9.
Yeah, 1:30 Eastern and whatever. It's 10:30 Pacific.
Okay, awesome. Thanks.
There is one question on Discord, Eric. If you have to, do you have to take a break? You can take a break. I can ask you later.
Oh, no, I can answer it now. Sure.
The question is, what is exactly the conservatism of the projection method? Is it really somehow the degrees of freedom coming from a chi-squared, or like you said, it's conservative, but and it doesn't adapt to the gap in the means. But maybe could you say anything more about how bad it really is?
Yeah, in that case, it's not so bad, but there are cases where it really is quite poor. And I think part of the reason is that I think maybe I'll draw a picture. Maybe one thing that kind of happens. Let's draw this. Okay, so suppose I have I have a joint confidence region like this for 2 parameters, right? Okay, and I want a confidence interval for this parameter here. So let's just say this is like theta. I'm not an artist. Sorry. Okay. Right. But let's suppose I have a pretty good guess of what alpha is. I think alpha is here, and I plug it in, and then I say, okay, well, here's my plug-in estimator for a confidence interval, right? Something like, it ends up being something like this. Okay. All right. But if I take a union, I end up with something like this. Sorry, there you go. So it ends up being much wider in general. And this kind of thing happens in higher dimensions.
Yes, I think part of the question, which I forgot to say, is the question was also like, can I take the union, somehow take the union differently to get away from the problem?
You can, and we will, in just like 3 slides.
Oh, okay, good.
Yeah, yep. Another question here is the max of means typically the right goal in practice? When is the max median or worst case performance? I think the max of the means I picked as a toy problem that just illustrates a bunch of the problems we're going to see in the later sections, as opposed to something that kind of shows up commonly. I mean, it does show up if you were taking the max, because if you took the maximizer of the means as your selected treatment, then that would be of interest. But I also should say that I picked it because it's going to show up in the value function and the Q function and other things. And so that's really, I just picked it because it was the simplest case that illustrated all these issues, and so that they don't look too unfamiliar when we get to them. That's the real reason.
I do have at least one question. Are there any papers that would actually look at finite sample bounds and confidence intervals for the max of means, at least for the Gaussian case, and show some kind of adaptivity? I've been thinking about this problem quite a bit, and I haven't found anything yet, but maybe there is something out there.
If you assume everything is normal,
yeah,
I think you can make progress in that case. Certainly in the 2-parameter case, I think people have worked out what the distribution is of the max of those 2 means analytically. I don't know if they've done it for more than 2, so that may be somewhere to start. So you could actually get the distribution of max of X bar 1 and X bar 2 analytically. So there's a paper in like it's in like IEEE transactions.
We want to estimate actually things, so that goes back to whether that's the right way of estimating things. So think about when the 2 means are within this 1/√10 distance of each other, then you would want to merge the 2 samples and to take the grand total mean, and then you would get much better accuracy and much smaller confidence intervals. So I think that's really the issue, that you don't want just to run with the max of the 2 empirical means. That's not what I meant. What I meant.
Oh, I see. Okay, I misunderstood you. Sorry. Yeah. Okay. I don't know if there's been much work on this. One thing I have seen, I think at a talk at JSM, so this is pretty recent stuff, was this idea that like they had maybe this is helpful or not, maybe it's not. Sorry if it's not. They had 2 trials basically, so they had 2 samples, and then they wanted to detect whether or not they could combine the data or not, and they were taking a convex combination of the 2 statistics that was trying to be adaptive, and they were trying to deal with like sampling bias. It's not exactly the same problem, but they were trying to do that kind of so it becomes a pooled statistic in one case, and it becomes like just a statistic from one in the other case. So it's sort of a related idea, but it's not quite what you're talking about, I don't think. Now I'm trying to remember who that was.
Yeah,
I'll have to think about it. Yeah, so I don't know. I think the finite sample bounds are still pretty open, as far as I know. That, but I could be wrong. Yeah.
Okay. Pretty cool. Thanks.
Maybe should we pause on the live streaming for now and then have a 15-minute break before the next part?
That sounds good. I'm gonna go get a sandwich.